now we can go into introducing the actual rules for carrying out deductions in predicate logic. So let's look first at the introduction rule for the existential quantifier. The rule here is very simple. If you have an individual instance of a formula, say phi A, then you can replace that with x and bind the variable with an existential quantifier. The idea here is that you can always infer from some specific thing being phi to a general statement that there is a phi. An example would be, suppose someone says LeBron James is a basketball player. So A standing for LeBron James and phi standing for the property of being a basketball player. Well, if LeBron James is a basketball player, then you know there is a basketball player, whoever that might be. There is someone who's a basketball player. It doesn't matter who A was. We could have also said Dwight Howard was a basketball player. Any instance is sufficient to be able to existentially generalize. So A can be arbitrary. It doesn't matter that we were talking about LeBron James or Dwight Howard. Doesn't matter as long as there is a specific instance. We can go to the existential generalization of that. Moreover, x here is an arbitrary choice for variable. So we could have used y or z. That didn't matter at all. We just wanted to pick a variable. Here's an example of the existential generalization or introduction of the existential quantifier in action. We can reason from fb and gb to there is y such that fy and gy. So here, a statement like this, FB and GB, is saying something like LeBron is a basketball player and LeBron is tall. So notice it's the same object and we're predicating two different properties of it. Well, that means that according to our existential generalization rule, there is someone who is a basketball player and who's tall. There's also an elimination rule for the existential quantifier, but we're going to skip over that and come back to it later because it involves some complexity that's better put until later. For now, we're going to skip over to the elimination rule for the universal quantifier, which is also very simple. What you can do here is if you have the universal quantifier on a line, you can delete the universal quantifier and instantiate any arbitrary individual constant. Suppose this statement was, for all x, x is a physical thing. Well, if all things are physical things, then look around, pick any old thing you want, and it's going to be a physical thing. So the sense of the universal quantifier is that everything in our domain has this property. That's what this universally quantified statement is saying. So we can pick anything in our domain, and it's going to have that property. This could have been A, it could have been B, it could have been C. Elimination of the universal allows us, given a universal generalization, to infer a sentence that says of a particular thing what the given universal generalization says of everything. Here's a nice example of the elimination rule for the universal quantifier. Suppose we have an argument like so. All pro basketball players are well paid. LeBron is a pro basketball player. Therefore, LeBron is well paid. We can symbolize that like this. For all y, if y is a basketball player, then y is well paid. LeBron is a basketball player. Those are our two premises. And the conclusion we're drawing is that LeBron is well paid. Here's the derivation of that. We start by listing our assumptions as usual. Line 3 is a substitution instance of line 1. That is to say, we've dropped the universal quantifier and substituted in for the variables an instance, LeBron James in this case. Since we have the antecedent of this conditional, we can then use the arrow elimination rule to get the consequent of the conditional on a new line. This derivation indicates the proper strategy when thinking about using the elimination of the universal. Which constant should I use in the substitution instance? Well, you want to look at your goal sentences. Here our goal sentence is WL. So we use the goal sentence as a guide for which substitution instance to use. If we had put BS arrows WS, well, that wouldn't allow us to do anything at all. Since we have BL and we're going after WL, well, we use this substitution instance of L. Let's go to a more complex example. Here we have these two premises, and we want to go to this conclusion that there is a B. Here's some example of some more ordinary reasoning that we might formalize in this way. Suppose someone put forward the following argument. If prohibiting price gouging is a government power, then everyone is safe from price gouging. Prohibiting price gouging is a constitutional power, therefore someone is safe from price gouging. It's a little bit of an odd argument, but you can see that this instantiates that form. So we can give a formal proof of the validity of that reasoning. What we do is, of course, as always, we start by listing our premises as assumptions. So we have two premises here. Both of these are going to be listed as assumptions. And the goal, again, of a deduction is to say, if you assume these things, then here's what follows. First step, we're going to use the elimination of the universal to get a specific instance of this general statement. What we've done is we've dropped the universal quantifier and we've replaced the resulting free variable x with c. Since one of our premises is that AC, we now have the tools we need to use a arrow elimination. Since we have the antecedent of the arrow statement on line 2, we can then disconnect the consequent of the arrow statement and write it all by itself on line 4. That was our elimination of the arrow rule. Now we're in a position to use the existential generalization. That is the introduction of the existential quantifier. Since we have one witness, C, of being B, we can say there is a B. C is a B, so something is a B. That's our introduction of the existential on line 4. So this proof is an example of using both the elimination of the universal and the introduction of the existential.